Why would you resign? Or why would he resign with you knowing he's not employed?
Why would you just trade Brady? Why would you just leave, get rid of Brady?
Because Brady is he literally is detained.
I think it's some money. More than anything.
Money.
You pay Brady way less. And that to me means something.
I think it's so funny.
Welcome to a Cisco meeting. You are entering the meeting now.
Okay. All right. Okay, we can get started for today's lecture. So finally we moved on to chapter 3. Last part of this lecture we'll talk about rubber elasticity. So with the next 4 lecture we're going to talk about what is rubber elasticity and how we can take advantage of rubber elasticity for many applications, okay? So when I mention rubber elasticity, what comes into your mind? Tires? That's a good call. That's probably one of the bigger part of the application for this. Anyone, any more thoughts? Elastomers. We have a lot of elastomers is fall into this rubber elasticity topic. So we're going to talk quite a lot about, not about specific material or chemistry, but talk about how can we understand rubber elasticity from a polymer physics perspective, okay? So let's get started. So to introduce you guys about the rubber elasticity, we need first to understand some fundamental concepts. There's a couple of them we need to talk about. First is viscoelasticity. So we want to discuss what is viscoelasticity. Have you guys studied in engineering courses? So Dr. Naz already taught about this. So viscoelastic property talks about the property that it's both viscous and it's elastic. So I think this is a very unique property to the polymer. And this is one of the favorite example when we go to a field trip to go to elementary school to do outreach. We show the rubber elasticity. So everybody can read what's a meaning of rubber elasticity, right? Viscoelasticity in terms of what the text means, right? So a great example is silly putty, as those 2 pictures show you. The material can potentially flow, and if you hold it in your hand for long enough time, it will change shape, just because it's a relative value between the time of the deformation versus the time of observation, okay? So in the shorter amount of time of observation, they will behave like solid-like. A good example is if you pull silly putty very rapidly, it will fracture elastically, okay? You can break it in the center and it looks like just a piece of solids. So on the back, if you observe for a long time, think about pulling it and deforming it as a time scale about seconds. If you extend the observation time scale from seconds to minutes or even to hours, then you start to see flow behavior of the material. For example, if you think about a silly putty like this, it will change. So there's quite a lot of things you can. The polymer physicist has been studying these class of material to understand. So there's a lot of parameter we listed here. There's viscosity comes into play, And there's a lot of interesting property related to this class of material. There's shear thinning effect, which means when you start to deform it, it will be much more easier to deform. There's also potentially shear thickening, or can also be Newtonian liquid, okay? The entangled system is more interesting. I won't talk too much about this. This will be Dr. Yung Simon's class next year. You guys will learn how the entanglement comes into play. That's a unique property of polymeric material. You know, when you entangle, then your material shows very unique property. If there's no entanglement, the polymer can be very brittle. Think about what holding these single crystals together are van der Waals force. So if you deform the crystal, they're just going to be brittle and break. Well, entanglement gives a unique property, okay? And on the right hand, you can see the thermodynamics and chain conformation comes into play. What these are quite interesting, but they're still different with what we're going to talk about today, rubber elasticity. So rubber elasticity is different from viscoelastic. You can think about a great example or major differences. If you buy a rubber band, you want to tie your hair, like I know a lot of students need that in the morning. So when you put a viscoelastic material in a rubber band, what's going to happen? You're not going to hold it into the shape. It's going to lose. Maybe in the morning, you look very shiny, hair is all tied up, but afternoon, it's going to break up. So a unique difference between viscoelastic and rubber elasticity is one of them is related to reversibility of elastic property. So if you look at viscoelastic material, it's not reversible elastic. So elastic region is only the first few percent of deformation. In other words, if you deform those material a little, stretch it a little, let it go, it will come back. But if you stretch more than few percent, let's say 2-3%, think about chewing gum. You pull it twice the length, let it go, it's going to stay there. It's going to stay elongated. For the rubbery material, you typically expect the material to be able to deform up to 300 or 400, even 500% of strength, and it will come back if you release force. Okay? And this chapter's lecture is mostly centered around how can we understand stress-strain behavior. Everybody should know a little bit about stress-strain, right? Dr. Naz has taught the class. Last year, it was a student's feedback is some of the fundamental concepts between mechanics is already taught, so I will do some introduction this year, but not everything, okay? So what makes elastomer interesting? Where you can think about elastomer in terms of application? I already heard Lena talks about the tire, Sonia talks about the other elastomer, and there's many other areas that requires rubbery material. So even our drinking cup, right? Everybody knows there's a seal in that. In the material, it's made of usually kraton elastomer, or a lot of time PDMS is also used quite a lot in other areas to create the seal. So you need these O-rings to make the seal. And one of the great story about elastomers, made elastomer famous, is the tragedy about Challenger's space shuttle. There was an argument between a lead scientist saying you cannot use this elastomer O-ring because in the outer space it's not going to be elastomer. It will not seal your fuel because they didn't understand the concept of glass transition temperature that well. And when you elastomer is cooled really below its glass transition temperature, it can be brittle. It will lose its elasticity ability. Okay. too bad the boss doesn't listen. It happens a lot of time. And always going to be a brave engineer jumps out and telling it's wrong, but nobody listens. But eventually they found that's the case. So it's a great example illustrating the importance of elastomer. Okay. So how does it link to today's lecture? So there's two properties you need. First, you need the material to be above glass transition temperature for elastomer. So elastomer tend to have low Tg. So a lot of time, think about PIP or natural rubber, isobutane. Those are with very soft backbones. Okay. So if you think about these molecules, so this backbone is very soft. If you put a polystyrene there, it's not going to be elastic, right? You need them very soft. PDMS, are those a good example? The second is they need to be able to be cross-linked. That's the second characteristic versus this one. If you put a melt, you can argue if you just need a material to be above its Tg, you can also make polystyrene to be an elastomer. You just heat it above its melting point or glass transition temperature. In that case, 100 degrees, but you're still not going to have reversible, because when you pull these chains, they're going to deform from a Gaussian coil to be elongated. And if you don't cross-link them in these points, they're just going to slide past each other, create a permanent deformation. That's kind of another linked to what a viscoelastic material is. So a lot of time we need to also have a cross-links. And anybody know what's the story in the early days, how people make rubbery material? What would be the first elastomer people make in the early days, or one of the most important ones?
Was it made by nature?
Yeah. So it's natural rubber, so it's coming from a rubber tree is very popular in the Southeast Asia, especially in Malaysia. It was one of the key strategy resource for the Second World War. So there was a long story about how Japan and the U.S. was battling in the southeast part of Asia, and they were fighting. Part of the reason is just for different value of life, right? The other reason is they trying to secure the access to those type of material. So natural rubber is polyisobutane, and they would put it in sulfurs to cross-link them, and that was one of the oldest way people make elastomer. You added the sulfur, there's an unsaturated bond, and at higher temperature you would create these cross-link points. Okay, so show us here. For a long chain, the molecular weight could be very high, up to 1 million. And at different spots, it would randomly cross-link with other material. So now if you think about, you can deform these, they would elongate. But because we are all locked with each other by this covalent bond, there is no way you can, this point to be slide past each other. So when you release force, we will teach you in more detail, the elastomer will relax back. Okay? So that's the key two of reasons why you need a cross-link network as well as a cross-link network as well as very low glass transition temperature. Okay? So that's kind of a generic design rule. And there is also other new elastomers made of interesting concepts. So this one is made of covalent bonds. Is there a way we can make elastomers not have physical crosslinks? Supermolecular. That's an interesting idea. You should be able to. So instead of have a covalent bond, you can have non-covalent bonds, which tend to be much weaker, right? So it's probably have a good elastic property at very low degree of strain, but you will still likely to have this, hysteresis. But there is another concept has been widely used. You guys should have known. So we have two polymer class. Dr. Patton teaches one, I teach the other one. What would be it? Any thoughts?
Hydrogen bonding? Or was that with the other one?
The hydrogen bond is similar. We all call these non-covalent bonds, right? You don't have covalent bonds. So how about ionic bond? Okay, can we make it more simpler? We don't need a bond. As I allude to you guys, we teach as polymer physics. Is there a physical way you can cross-link? Hmm? Van der Waals? Entanglement? Oh, getting close, but not there yet. No, neither. So how do you make the material temporary cross-linked without moving?
Increasing the temperature?
Maybe crystallization is one way, but it's very hard to control. How about just make it a glassy? Okay? So if you can make the domains made of a block which is glassy, so that's the story about how SEBS, styrene, ethylene and styrene triblock polymer comes into play. So you have two ends made of glassy material. Glassy means at room temperature it's rigid, it's not moving. Okay? So you basically make triblock polymer. They would self-assemble and creating those glassy points between different chains. So you can think these end group as the anchoring point and basically fixing all the chain in the place. So when you start pull the material, it will be elastic as well as room temperature. And this called is thermoplastic. So it can be moved and it can be changed at higher temperature. In other words, if you heat it above glass transition temperature polystyrene, now your network is start being flowable or movable again. Helps you to process the material. But if you cool it down again at room temperature, the polystyrene becomes glassy again and it won't move. So which is trying to show here. Of course, the entanglement will play a role, but it's only will make your material viscoelastic. Okay? So, elastic response. I'm feeling studying this slides to the next few. I'm repeating what Dr. Nance has been teaching you guys, so I'll speed up a bit. So, what's the characteristic about elastic deformation? Reversible, right? So, what is? Think about this as spring. If you now load something down there, the more material you put on, the spring will go deeper, right? And if you watch this curve, this is force versus displacement. So how much force you need to pull a spring? Displacement means how much they're being deformed. Or in polymer world, or in mechanics, we usually call it stress and strain. If you divide the force by the cross-section area or displacement divided by original film length, okay? Elastic means this is going to be straight. And what is slope called? All right. That's right. If you plot stress and strain, that's Young's modulus. In this case, it's a spring constant. But they're telling you the same thing. How hard you can deform a material. So Young's modulus, everybody should know. What's a typical Young's modulus for polymer? Let's say polystyrene. What's the unit for Young's modulus? Pascals, right? It should be pascals, which is the unit for modulus. So the higher the modulus, what's the property of the material? More rigid. So I'll give you guys a few range to think about. What's the value you think about kilopascal, megapascal, gigapascal? gigapascal, which is very common for glassy material. Okay, so I want you guys to have a little bit of concept. So polystyrene is about 3 to 4 gigapascal modulus. And if your material is much softer, your modulus will be lower. Now, think about what would be the example of softer material. How about PDMS elastomer?
Kilopascals? 0.1 gigapascal?
All right, that's not the right answer. It was a good trap. So it depends on cross-link density. And we will talk about how does cross-link density affect modulus. Because the elastomer is very broad. It can be made very soft or made very rigid. But typically, they're only on the order of tens to hundreds megapascal. Some of the soft ones can be even lower. So there's an interesting professor in Berkeley. His research topic is very interesting. He studies aging effect on human skin's modulus. So I think it's great and very important for all the cosmetic products. So when you're born, let's say my little son Maxwell, what is his elastic modulus for his skin? Guess? How much? No way. Your skin is not going to be as rigid as polystyrene. Touch this. So they are much softer, right? But typically it's on the order of 100 kilopascal is the range. So it's slightly softer than the PDMS elastomer, okay? And anybody knows in those Hollywood movies, what do they use to make face shifting?
Wax.
Wax? No, come on.
What was that?
Some part, maybe not.
It was the Stephen King movie back in like 92.
Okay, what is it called? So they have actually a brand called Ecoflex, ECOFLEX. It's made of a material, a very lightly cross-linked polymeric material. So the modulus they made is such that it matches with modulus of your skin. So your skin is typically on the hundreds of kilopascal. If you put polystyrene on it, when you smile, you know, polystyrene not going to do anything. You just have like down face, like poker face, right? So if you put an Ecoflex, it will basically deform whatever the way you're going to do, right? It will match the modulus value. And even softer would be tissues in your body. So think about the lungs, the muscle, the fats. They typically are on the order of kilopascal, so 100 times softer. So most of the human body is made of softer tissues, except all these bones. They're hundreds of gigapascal level. So quite a miracle. You blend soft and hard, and they work very seamlessly together. So coming back to this topic, we need to get some rough idea what's the modulus for various polymer, from rigid, polystyrene, etc., polyimide, to even more rigid would be carbon fiber is a good example. The modulus usually runs about 100 times higher than polystyrene, so hundreds of gigapascal. If you're going to go even higher, there's an inorganic ceramic material, or even, you can name it, the ghost ring, or I wouldn't say man's like nightmare, but diamond. That costs the same. It's the same piece of element. It's just carbon, and it's 1 gram costs so much. You might heard nowadays people can grow them in the lab. Yeah, and they cannot tell the difference. Even the major company like DBS, they have their own brand called I think Lightning Box. Now they can sell you like $600 for 1 carat. Looks exactly the same, even more pure, right? But those are on the pinnacle of modulus. They are the highest. So how do we define different deformation of the material? So I'm pretty sure Sergey probably talked most of it. So this is the most common one, tensile. when you pull the material, you're trying to understand what is the response of the material. So they're going to be force holding the material together, and you measure how much force being applied. This is commonly used in strong, where you clamp to side of material, then you torque your head out of it. You just pull it until it breaks. In the mid-century, if you were judged by the king, you might be putting between hoses and being pulled apart, which is miserable and terrible, right? Compression force. This is where you compress your material and study what is force you need to compress it. And the modulus for compression versus tensile are different. They're related, but they're different. Okay, we're going to talk about it. The other few are less discussed, but I think shear is discussed more. This is usually measured in rheometer, in which you actually have two discs going parallel with each other, and you put your material sandwich in between, then you start to apply shear force and measure what's the response coming from the other plate, okay? Or you can think about if we put a jello there, now I'm going to move the top while fix the bottom. The modulus for this version is very different from the other two as well. Then we have torsion and deflection, okay? But most of the time, we actually would discuss the first, second, and last one in terms of their modulus. And this is called Young's modulus, compression modulus, and shear modulus. And they are linked by Poisson ratio. And we will define what that term is in a few seconds, okay? All right, so this is we have already kind of discussed at the beginning, where I mentioned there's two ways you can make elastomer. So the first way is covalent cross-linked. So you throw these linear chains, and you add a crosslinker, and they would cross-link them randomly at the point where they come in together, the crosslinker, as well as polymer. And in the textbook, you will see they start talking about different ways they would cross-link. You tend to have creating these dangling endpoints, loops. And there's a lot of dispersity in terms of how they cross-link. Area you would have these two chains happen to be cross-linked shorter together. There's an area that you create a very long chain. For example, this one. It's all going to come into play later in the modulus, and we will talk about that. And this is permanent. So once you form the elastomer, you cannot disentangle it. The second way is physical cross-link, either by these non-covalent interaction. You guys already discussed all kind of possible interaction. Hydrogen bonding. Van der Waals forces are much weaker. They're not likely to create it. Okay, hydrogen bonding is very commonly used. Coordination bond is another very weak bond. Metal polymer. Hydrogen bonding is not too strong, right? You can re-break and make them reform, and there's a lot of literature reports about self-healable elastomer. If you cut the elastomer into pieces, you put in contact again, they actually would self-heal and restore their elastic property. Quite amazing. And I saw there's recently patents about self-healing phone screens protector. I want to give it a try. I haven't got a chance. But the promise they have is if you scratch it, then give it a longer time, those non-covalent bonds will reform and create similar property. Okay? But I have to be honest with you guys, this is still like most commonly used because it's much cheaper to make. This is like dominant technology, as well as SEBS, using physical glassy crosslink points. Okay? So, excuse me. So mechanical deformation. Now we're going to talk a little bit about what is stress and what is strain is. Some fundamental definition. I believe Sergey, Dr. Nazarenko has already talked about that, so I will briefly discuss. Stress is where we define by the force applied to a given area. So this will be equal to F divided by A. And this is the unit. Force is given by Newton. Area is usually given by meter square. So you would have a Pascal value. Okay. So this he probably already talked about. There's strain stress and stress tensor, and different ways of you have tensile stress as well as shear stress. So this can be generalized by a force applied to a surface, and you would have deconvoluted as 3 different components, right? If the force is not normal, you can deconvolute it to be sigma out xx. This is the force normal to this surface. That is a tensile force. And you have 2 shear force, sigma xy and xz, applied to the different direction. All these will play a role when your material is being deformed. So when your material start to be deformed, they will show you different values over this. Okay? Okay, next we need to define what is strain. I assume everybody knows. Can everybody tell me what's the difference between the lambda, the draw ratio, as well as strain, sigma? I assume you guys all know. Oh, it's been a bit quiet. So how about strain? Everybody know what the strain is? So this is a little bit newer parameter we need to define for this class, it looks like. So strain defines by L0 is original length of your material. L is the final length after deformation. So let's say you have 1 centimeter long elastomer. You pull it to 1.5 centimeter. Strain would be 1.5 minus 1 divided by 1. That will give you 50% of strain. Okay? So how much delta L, or change it in the length, divided by original length, right? As we said, our deformation is about 0.5 centimeter. Our original length is 1 centimeter. And if you divide them, that gives you the strain. There's also, in the tensile stress, we also define another term called jaw ratio. Jaw ratio is defined lambda equal to L divided by L0. L is the final length, L0 is original length. So what would be the jaw ratio for the system like we just talked about? You have a 1 centimeter long sample elastomer to form to 1.5 centimeter. That's right. So how do you relate these two terms? Are they somehow linked? So lambda would be equal to
Strain minus 1.
Strain plus 1. Plus 1, right? So this is just easy when you have a large degree of deformation. Strain they can be used in many cases interchangeably. But in classical polymer mechanics, it's usually defined by strain, okay? Oh, this is an example. So everybody understand this? If we now have a film, elastomer has deformed 3 times of original length, what's the strain? 200%, they're the same, right? And what is the draw ratio? 3, right? Easy cheesy. All right, so now this is about mechanical deformation. So in comparison with the first example we give about a spring and how we load the spring, you would have a spring constant where now if you have F, force applied to the material, you have a certain deformation in the X. X is displacement. In the Hooke's law, basically for metal spring, you would have force would be equal to K multiplied by X. K is called spring constant. So if you have a spring, you can kind of feel it, how much you press it, is proportional towards the force. This is one very simple way. We know metal spring is used almost exclusively in many application space. In car suspension, in your ball pen, even in some of the shoes in the early days for the basketball player, or even in your mattress is where you sleep on. It can be elastomer or spring loaded, right? Similarly, for polymer, we have similar phenomenon. So a strain of example is proportional to the stress. So we can also define Young's modulus term here. So your stress is proportional to the strain. Okay? So they are very much similar. So E in here is defined as Young's modulus. So if you define your deformation is not elastic tensile, if you share it, you would also have a stress applied to your sample, strain applied to your sample. But if you're in the shear geometry, you would have a shear modulus. Shear modulus is typically defined as G. Okay? And you must have already learned there's a storage modulus and loss modulus. One is G prime, the other is G double prime, characterized in different ways of your deformation. Compression modulus is how it's being compressed and defined as by K. And we will talk about how they will be linked with each other. Okay? Well, this is a classic example. Very general. There's no material attached. So you apply stress and strain, you would have this behavior. Please note this is not a strictly elastomer. This is not a strictly elastic deformation, because otherwise you would only have a straight line. So I want to pull your attention to several different regions. The black curve is what we have measured. There is also two parameters we need to talk about. So as you can see, this is not a linear line. If you have a pure elastic behavior, even for the polymer, you should have a linear stress strain curve. But as you can see, when the strain goes up, your polymer stress starts to plateau. Why is this? This typically happens when your material is not purely elastic. There is some viscoelasticity comes into play. So it could be that when you release from that, it will not go down to the original length. Okay? So in this case, you should only treat the first initial 0.005 or smaller as elastic region. Okay? You get the modulus from here. And the other way people commonly use is called 1% or 2% of modulus, where you basically look at this range. But elastomers typically will be relatively linear in the first few percent. Okay? Now, let's define the second term, very important for everybody. It's called Poisson ratio. Everybody, tell me a bit. Have you ever learned this concept already? Okay, we don't need to go too much detail. It talks about how the deformation perpendicular to the primary deformation direction versus primary strain, right? So for elastomer, that's what I want to point you out. For the elastomer, the Poisson ratio is 0.5. Okay, that's actually is a number that will give you material is not compressible. So in other words, if you compress in one direction, it changes the other direction. So you always have constant volume. This is the equation I mentioned at the beginning, where you now has correlation between the elastic modulus and shear modulus. So for the perfect elastomer, if you look at V equals 0.5, elastic modulus will be 3 times of shear modulus. Okay, These are some of the characteristics, keeping that in mind. Otherwise, there's not much to say, except elastic modulus is 0.5. Plastic deformation means your polymer will permanently deform. It's not follows the constant of volume. You can think about plastic deformation as the example we talked at the beginning. If you have chewing gum, you pull it, it deforms and never comes back. Okay? In this case, your Poisson ratio will be lower. I don't need to go too much detail here either. This is a very typical ways to describe polymers, and we want to tell you the difference between the engineering strain and the true strain. Everybody knows the difference? The difference is how we define, how we consider a cross-section area difference during the deformation, okay? If you look, this is an example where you have a stress strain. This is can be seen for polycarbonate. Polycarbonate is no material, they have necking behavior. What this means, if you create dog bone sample, when you pull it, it will show a narrowing region and it will not fail, but it will continue to grow the length of that region. So when we apply the stress strain curve, the engineering strain says this is what the force divided by initial cross-section area, okay? Which is given by, I don't think it's detailed here, but you can think about if you measure how big the cross-section is and you can divide by that. But you measure the force divided by initial section area. When the neck forms, you actually, the force sensed by the intermediate region is higher. Just because we divide by a larger area, the value is not exactly correct. So we need to take that into consideration. It's quite easy. If it's elastomer, you just need to multiply by the Joule ratio in here. In other words, true stress is engineering stress multiplied by the Joule ratio. Okay? And most of the time, people plot just the engineering stress versus the engineering strain, unless your material has a lot of changes in the cross-section area, like necking or deform to land are very high. So elastomer is an example where you can pull the polymer up to 500% straight. So 5 times longer than original length. Then your cross-section area would change quite a lot. So even there drop in force, don't be fooled by it. You actually will have a much higher true force in the sample. I think that will be it. The next class we will start to discuss how do we understand different deformation between metals and polymers. So let me go back to one slide. So everybody knows what makes a polymer unique, right? So if you hang 2 pallets of gold nuggets there, nobody gonna steal it from you, but you hang it from a spring, and side by side you put a rubber band, take this 2 of the material same. You can make these metal spring and the rubber band the same modulus, so they would deform the same way, right? Now there's a very interesting phenomenon. It's called polymer rubbers would respond totally differently to the temperature versus a metal. So let's say, like today, I pull these 2 strings hand in hand, walk outside, it's freezing outside. These 2 would behave very differently. Actually, the metal one, do you think the spring will contract or expand when we go out to a much lower temperature? Will contract. How about the polymer?
Depends on the
Longer. So in other words, there's an interesting phenomenon. If we plot temperature modulus, Well, this is a high temperature, right? Let's say this is room temperature, this is minus 50. So E is modulus for the polymer, K is modulus for the spring. So your K value will go down with the temperature, or go up versus the lowering the temperature. So if I take this thing outside, the spring constant will be higher. Since our weight is constant, it will retract, okay? Or if you put this in the oven, your spring will relax and it will get longer. Well, the polymer takes a totally different trend. So polymer will show up as the modulus would go up with the temperature. So your modulus will depend on the temperature and will be very different. It's quite a contrast between these two. And we will explain the mechanism in the next class and explain to you why they would behave that way. Okay? And what I can tell you is that deformation mechanism is very different. This is enthalpy driven, or how for the metal depends on intermolecular add-on forces, and this is the entropy driven, where it depends on the entropy of a chain being stretched. Okay? If there is the only thing you want to learn in this chapter, it might be this interesting fact. All right? So we will come back on Thursday.
So we have a quiz posted on Canvas, but it doesn't say the date. Is that going to be more likely to be Tuesday or Thursday of next week?
So it will be next week at least. Okay. So likely to be next before the Thanksgiving.
I'm going to email you about maybe meeting the Wednesday before the quiz to talk over that.
No problem. Yeah. Yeah. So Mark, when are you leaving?
We're heading out tomorrow after class.
Tomorrow? Okay.
Yep.
Good.
Yep.
Enjoy. Mm-hmm.
Can I check my second one?
Oh, you have not? Yeah, of course.
I missed last lecture.